The company that built an empire on artificial intelligence just made a move that has quietly started a completely new hardware war, and almost nobody outside the industry noticed the moment it happened. NVIDIA didn't get to $1 trillion valuation by accident. It built a compute moat so deep that switching away from its chips became almost unthinkable for the world's biggest AI labs. Now that same company is pointing its entire playbook at quantum computing, and the early signs suggest this next battle could be even bigger than the one that made Jensen Huang the most powerful person in technology. Stick around, because by the end of this video, you'll understand exactly why this shift matters far more than most headlines are giving it credit for, and why the outcome of this quiet war could end up shaping which companies control computing power for the next 30 years. It's also worth noting just how unusual this current moment feels compared to earlier chapters of NVIDIA's history, because the company built its AI empire over roughly 17 patient years, largely outside the public spotlight, while its quantum empire appears to be forming in a fraction of that time, under intense public scrutiny, with every major move analyzed in real time by investors, journalists, and rival companies alike. The compressed timeline changes the competitive dynamics considerably. Rivals who were caught flat-footed by CUDA's rise, because almost nobody was watching NVIDIA's software strategy closely enough back in the mid-2000s, don't have that same excuse this time around. Every major tech company now understands exactly what NVIDIA is trying to do in quantum computing, because they watched it happen once already with AI, which means this hardware war is unfolding with far more informed, far more urgent competitive responses than NVIDIA ever faced during its original rise. Let's start with how NVIDIA actually built its AI empire, because understanding that story is the only way to understand why its quantum move is so dangerous for everyone else in the industry. NVIDIA didn't just sell fast chips. It spent roughly 17 years quietly building CUDA, a software platform that let developers program its graphics chips for general-purpose computing long before anyone cared about deep learning. Back in the mid-2000s, this looked like a strange, almost pointless investment. NVIDIA was a gaming company known for graphics cards that rendered explosions and character models in video games, and pouring years of engineering resources into a general purpose. Computing platform seemed like a distraction from its core business. Wall Street barely noticed, and most of the tech industry viewed CUDA as a niche tool for a small community of scientific computing researchers who needed more horsepower than traditional processors could offer. Even inside NVIDIA itself, some executives reportedly questioned whether the continued investment in general-purpose computing software made sense for a company whose core revenue still came almost entirely from selling graphics cards to gamers, a tension that persisted internally for years before deep learning validated the strategy in dramatic fashion. The turning point came gradually at first, and then all at once, the way most genuine technological shifts tend to unfold. A handful of academic researchers working on neural networks discovered that CUDA's parallel processing architecture, originally designed to render millions of pixels simultaneously for video games, happened to be almost perfectly suited to the kind of massive matrix multiplication operations that deep learning models require. What started as a niche academic curiosity within a small research community gradually attracted attention from larger labs, then from major technology companies, and eventually became the foundation that essentially the entire modern AI industry was built on top of. Then deep learning exploded, and it turned out CUDA was exactly the software layer every AI lab on the planet needed. NVIDIA already had the software ecosystem every major lab needed, with millions of developers, thousands of optimized libraries, and native support baked into every major cloud platform. That combination created what analysts now call a compute moat. And it's the real reason NVIDIA commands roughly 85% of the entire AI chip market today, with revenue projections pushing toward $1 trillion by 2027 through its Blackwell platform alone. This wasn't luck. It was the direct payoff of patient infrastructure investment made nearly 2 decades before anyone else understood why it mattered. It's worth pausing on just how difficult it has proven for competitors to close this gap even after fully understanding what NVIDIA had built. Recognizing a moat exists and successfully draining it turn out to be 2 very different challenges entirely, and the AI chip industry over the past several years has offered a clear demonstration of exactly how stubborn ecosystem lock-in can be, even when rival companies throw enormous resources at the problem with full knowledge of what they're up against. Competitors have tried to break through this moat for years and mostly failed. AMD's newest Instinct chips deliver competitive performance on specific workloads, particularly inference and fine-tuning tasks, and have started attracting hyperscalers looking to diversify their supply chains away from total NVIDIA dependence. But its OCM software platform still lags CUDA badly in developer tooling and library support, and that gap has proven far harder to close than the raw hardware specifications alone would suggest. Intel bet on its Gaudi chips, promising faster training and better efficiency, but commercial adoption badly underperformed expectations. And Intel eventually canceled its planned successor chip entirely, pivoting to a different rack-scale strategy instead. Even Google, with its own custom TPU chips powering its internal AI research and reportedly offering rival labs access to up to 1 million of them, still can't match the sheer developer ecosystem gravity NVIDIA has built around CUDA over nearly 2 decades. This is the empire NVIDIA is now defending, and it's exactly why the company can't afford to sit quietly while a new computing paradigm potentially rises up beside it. That paradigm is quantum computing, and here's why NVIDIA suddenly cares so much. For years, Jensen Huang publicly downplayed quantum computing, joking as recently as early this year that the technology was still at least 2 decades away from practical use. But somewhere between that joke and today, the roadmaps from major quantum companies became aggressive enough, and the underlying breakthroughs credible enough, that NVIDIA completely reversed course. This reversal wasn't subtle either. Within the span of roughly a year, NVIDIA went from publicly dismissing quantum computing as a distant curiosity to building some of the most important infrastructure in the entire quantum industry. A shift so abrupt that even seasoned industry analysts struggled to fully explain it at first. The company built the Accelerated Quantum Research Center in Boston, packed it with its most powerful GB200 rack scale systems, and partnered directly with Harvard and MIT's leading quantum physics labs. It released NVQLink, an open architecture connecting quantum processors directly to GPU computing power, and rolled out Ising, an entire family of AI models built specifically to calibrate and error-correct fragile quantum systems in real time. The scale of adoption already happening suggests this strategy is working faster than almost anyone expected. 9 major national laboratories have already connected into NVIDIA's quantum network, alongside 17 different quantum hardware builders spanning superconducting, neutral atom, and photonic architectures. Harvard's engineering school, Cornell, the University of Chicago, and research institutions across multiple continents have adopted NVIDIA's Ising models within months of release. That kind of rapid, near-universal adoption across competing hardware approaches is exactly the pattern that preceded CUDA becoming unshakable inside the AI world. And it's happening again right in front of us. Let's look at some of the specific names involved here, because the breadth of this adoption is genuinely remarkable once you lay it out. On the national laboratory side, NVIDIA's NVQLink network already connects Brookhaven National Laboratory, Fermilab, Lawrence Berkeley National Laboratory, Los Alamos National Laboratory, MIT Lincoln Laboratory, Oak Ridge National Laboratory, Pacific Northwest National Laboratory, and Sandia National Laboratories. These are not casual research partnerships. These are institutions with decades of history working on the most sensitive scientific and defense-related projects in American history. And their willingness to build core infrastructure around NVIDIA's platform signals a level of institutional trust that took the AI industry years to develop toward CUDA. On the commercial quantum hardware side, companies like Quantinuum, Quera, Quantum, Machines, Atom Computing, IonQ, IQM, Quantum Computers, and Inflection have all integrated NVIDIA's tools into their development workflows, spanning nearly every major physical approach to building a working qubit currently being pursued anywhere in the world. This breadth matters enormously for the hardware warframing because it means NVIDIA isn't betting on a single winner. It's positioning itself underneath every horse in the race simultaneously, which is precisely why competitors are finding it so difficult to route around NVIDIA's growing influence, regardless of which specific quantum technology eventually proves most commercially viable. To put a finer point on just how comprehensive this adoption has become, consider that the calibration side of NVIDIA's Ising models alone counts adopters spanning Taiwan's Academia Sinica, the United Kingdom's National Physical Laboratory, and multiple American startups working on entirely different physical qubit approaches. The decoding side reaches even further, pulling in universities across South Korea, Southern California, and the American Midwest, alongside specialized quantum companies most casual observers have never heard of. This isn't the pattern of a company carefully cultivating a handful of prestige partnerships for marketing purposes. It's the pattern of a company racing to embed itself into as many corners of an emerging industry as physically possible, before competitors have a chance to establish rival standards that could fragment the market and dilute NVIDIA's influence. There's real tension building here too, because 2026 is being called a genuinely crucial year for the entire quantum industry, with major manufacturers racing to move from pure engineering demonstrations toward actual practical utility. Photonic quantum companies are pushing toward large-scale system integration in facilities spanning multiple continents. Superconducting players, like IBM, are targeting real demonstrations of quantum advantage this year, part of a broader plan built around a quantum-centric supercomputing architecture the company has spent years developing. Entirely new manufacturing approaches, including massive dedicated quantum chip fabrication facilities being built in Europe, are scaling production by a factor of 20 compared to current capacity. Every one of these competing approaches, regardless of who ultimately wins the underlying physics race, still needs exactly the kind of real-time classical integration NVIDIA has spent the last year aggressively building and giving away for FRIE through open models and open architectures. It's also worth noting how unusual it is for competitors, as fierce as Google, Microsoft, IBM, and NVIDIA, to all be racing toward compatible rather than mutually exclusive versions of the future. In most technology battles, one company's win is another's loss, but quantum computing's current structure means multiple approaches can coexist and even benefit from each other's progress, because breakthroughs in error correction, calibration, or fault tolerance tend to be broadly applicable across different qubit architectures rather than locked to a single company's specific hardware. This is part of why so many of these organizations continue collaborating openly through published research, shared conferences, and even joint infrastructure projects like the National Laboratory Network NVIDIA has built. Despite being fierce commercial competitors in nearly every other sense, it's a strange kind of hardware war, one where the participants sometimes need each other's breakthroughs to succeed, even while competing intensely for control over how those breakthroughs eventually get commercialized. Let's take a closer look at each of these competing approaches individually, because understanding the differences helps explain why no single company appears close to a decisive victory yet, and why NVIDIA's neutral positioning looks so smart against this particular competitive backdrop. Superconducting qubits, the approach favored by IBM and Google, use tiny loops of superconducting material, cooled to near absolute zero to create quantum states. This approach benefits from decades of existing semiconductor fabrication knowledge, since superconducting qubits can be manufactured using processes that share some similarities with traditional chipmaking. The trade-off is that these systems require extraordinarily expensive cooling infrastructure and remain highly sensitive to environmental noise, which is exactly the kind of problem NVIDIA's real-time error correction systems are designed to help manage. Neutral atom systems, the approach favored by companies like Quira and Atom Computing, use precisely controlled lasers to trap and manipulate individual atoms suspended in space using their natural quantum properties as qubits. This approach has generated significant excitement recently because it appears to scale more easily to larger qubit counts than some competing methods, and neutral atom systems have already demonstrated some of the field's most promising fault tolerance results, including breakthrough research emerging from Harvard's own quantum labs. Photonic quantum computing, pursued aggressively by companies racing to build ultra-large scale systems across multiple countries, uses individual particles of light as qubits instead of matter-based systems. This approach offers a theoretical advantage in that photons are naturally resistant to certain types of environmental noise that plague matter-based qubits, though the engineering challenges of reliably generating, manipulating, and detecting individual photons at scale remain formidable. Then there's Microsoft's topological approach with its Majorana chip, which takes a fundamentally different bet on the underlying physics itself, attempting to create qubits that are theoretically protected against certain categories of errors simply because of how the exotic particles involved behave, rather than relying purely on external error correction systems layered on top afterward. If this approach eventually works at true scale, it could sidestep some of the fragility problems plaguing other qubit designs entirely, potentially reducing the burden on classical error correction systems, like the ones NVIDIA has built its recent strategy around. This is precisely why Microsoft's progress here is worth watching closely, because a genuine breakthrough in topological qubits could shift some of the competitive balance in ways that don't automatically favor NVIDIA's current classical integration model, and it's exactly the kind of development that could force NVIDIA to adapt its own strategy far sooner than its current infrastructure build-out suggests it's preparing for. Each of these approaches has passionate advocates within the physics community who genuinely believe their chosen architecture represents the correct long-term path forward. And the honest truth is that nobody, including the companies themselves, knows for certain which approach will ultimately prove most commercially viable at true scale. This uncertainty is exactly why NVIDIA's strategy of remaining hardware agnostic looks so shrewd in hindsight. Rather than betting the company's future on a single physical approach that could ultimately prove to be a dead end, NVIDIA built infrastructure flexible enough to support all of them simultaneously, collecting value from whichever approach eventually wins without having to correctly predict the winner in advance. Betting on a single qubit architecture means accepting enormous binary risk, since an entire multi-billion-dollar investment could become worthless overnight if a rival architecture proves superior. NVIDIA's classical integration strategy carries far less of this binary risk, because regardless of which physical qubit approach ultimately wins, the fundamental need for extremely fast, extremely reliable, classical error correction and control systems remains constant across every single architecture under consideration. This is a subtle but critical distinction that explains why NVIDIA's leadership has been so willing to publicly commit enormous resources to quantum computing, despite genuine uncertainty about which specific hardware approach will eventually dominate. It's worth understanding why giving this technology away for free is actually the smartest part of NVIDIA's entire strategy, rather than a strange act of corporate generosity. When NVIDIA released its Ising models as open source, it wasn't sacrificing revenue, it was accelerating dependency. Every research lab, startup, and national laboratory that builds its quantum workflow around Ising and Q2Q becomes structurally tied to NVIDIA's ecosystem. The same way early AI researchers who built their first models on CUDA found themselves locked into that ecosystem for years afterward, long after cheaper alternatives eventually arrived. Free adoption today quietly builds the exact same switching costs tomorrow that turned CUDA into an unbreakable moat during the AI boom. This is a pattern investors who watched NVIDIA's earlier rise know extremely well. And it's exactly why some analysts are already describing NVIDIA's current quantum investments as a step change the market hasn't finished pricing in yet. This pattern of strategic generosity followed by structural lock-in isn't unique to quantum computing. And it's worth remembering how it played out during the AI boom to understand why it works so effectively. When NVIDIA released CUDA-related developer tools and libraries at low or no cost during the early years of deep learning, competitors dismissed it as a minor sideshow to the hardware sales that actually generated revenue. Years later, those same competitors discovered that ripping CUDA out of an established AI research pipeline was almost as expensive and disruptive as switching an entire company's operating system, because thousands of hours of engineering work, optimized code, and institutional knowledge had all been built specifically around NVIDIA's software stack. That lock-in effect is precisely what allowed NVIDIA to charge premium prices for its hardware, even when technically comparable alternatives existed at lower cost, because the true cost of switching was never really about the chip price itself, it was about everything built on top of it. The same dynamic is now unfolding in quantum computing, except potentially even faster, because NVIDIA learned exactly which levers to pull the first time around. Universities and startups don't need to pay licensing fees to access Ising or Q2Q. They simply need to build their research around it, which is exactly what's happening across dozens of institutions simultaneously right now. By the time quantum computing becomes commercially significant enough for switching costs to matter in a serious financial sense, an entire generation of quantum researchers will already have been trained, in a very literal sense, to think in NVIDIA's frameworks, use NVIDIA's tools, and depend on NVIDIA's infrastructure without ever having paid NVIDIA a cent for the privilege. That last point deserves a little more attention because it explains why this hardware war matters, even before quantum computing becomes commercially significant on its own. NVIDIA's core AI chip business has faced real turbulence this year, squeezed by export restrictions, affecting sales into China, and broader questions about whether massive AI infrastructure spending can keep accelerating at the pace investors have gotten used to. Quantum computing gives NVIDIA a genuinely new growth frontier, one insulated from many of the same geopolitical and competitive pressures currently squeezing its core GPU business. Even if actual quantum revenue remains small for years, the strategic option value of controlling this layer is exactly the kind of long-term positioning that historically pays off enormously for companies patient enough to build it early, well before the rest of the market fully appreciates what's happening. This financial dimension is worth unpacking a little further because it explains why so many analysts have started reevaluating NVIDIA's long-term growth story specifically because of its quantum investments. For years, NVIDIA's stock price has been almost entirely tied to the pace of AI infrastructure spending, meaning any slowdown in AI data center construction or any sign that hyperscalers might be overbuilding capacity has translated directly into stock volatility. Quantum computing offers something genuinely different, a growth avenue with its own independent timeline, driven by physics breakthroughs and academic research, rather than purely by corporate AI budgets. Analysts covering NVIDIA have started factoring this into their long-term valuation models, even while acknowledging the revenue contribution remains modest for now, precisely because the strategic positioning looks so similar to the early CUDA investments that eventually paid off in ways almost nobody predicted at the time. That historical pattern is exactly why so many investors are choosing to pay close attention now, rather than waiting until quantum computing revenue shows up clearly in a quarterly earnings report, by which point the most attractive entry point will likely have already passed. There's also a competitive dynamic worth examining here involving China, because the semiconductor industry has already been reshaped once by escalating trade restrictions between Washington and Beijing, and quantum computing appears headed toward a similar geopolitical framing. Export controls affecting advanced AI chips have already forced NVIDIA to develop scaled-down versions of its hardware specifically for the Chinese market, cutting into potential revenue and creating genuine uncertainty about the company's long-term access to one of the world's largest technology markets. China has responded by pouring enormous state-backed investment into its own domestic chip and quantum research programs, hoping to reduce dependency on American technology entirely. If quantum computing becomes the next major front in this broader technological rivalry, NVIDIA's early dominance in classical quantum integration infrastructure could become a genuine point of national strategic interest, not just a corporate business decision, especially if American national laboratories continue building core research infrastructure specifically around NVIDIA's platform. Meanwhile, the rest of the tech industry is watching this unfold with a mixture of admiration and genuine concern. Admiration, because NVIDIA's execution has been genuinely impressive, moving from a public joke about quantum computing being decades away to owning meaningful infrastructure across the entire industry within roughly a single year. Concern, because concentrating this much control over two consecutive foundational technologies inside one company raises real questions about competition, pricing power, and who ultimately gets to set the terms for how the next era of computing actually develops. Regulators who spent years scrutinizing NVIDIA's dominance in AI chips are almost certainly going to start asking similar questions about its expanding footprint in quantum infrastructure, especially if that footprint keeps growing at its current pace. This regulatory angle deserves closer examination because NVIDIA has already faced antitrust scrutiny in multiple jurisdictions over its AI chip dominance, with regulators in the United States, Europe, and China all raising questions at various points about whether the company's control over both hardware and software creates unfair competitive advantages for AI developers, who have no realistic alternative. If NVIDIA successfully replicates that same dominance pattern inside quantum computing, an industry still young enough that regulatory frameworks haven't even been fully developed yet, it could face intervention far earlier in the technology's life cycle than it did with AI chips, where meaningful scrutiny only began after the company had already become essentially unavoidable. Some policy experts have already started raising this exact concern, suggesting that regulators should proactively examine NVIDIA's quantum infrastructure investments now, while genuine competitive alternatives could still realistically emerge, rather than waiting until the company's position becomes as entrenched as it currently is in AI chips, at which point meaningful intervention would likely prove far more disruptive and far less effective than earlier action could have been. There's also an important distinction worth drawing between how NVIDIA built its AI dominance and how it's building its quantum dominance, because the two situations aren't perfectly identical despite following a similar overall playbook. When NVIDIA's CUDA ecosystem became dominant during the AI boom, it happened somewhat organically, driven primarily by developers voluntarily, choosing NVIDIA's tools, because they were simply the best available option at the time, with limited direct government involvement in that adoption pattern. The quantum computing situation looks structurally different because so much of the current adoption is happening through direct partnerships with national laboratories and government-funded research institutions, meaning public sector infrastructure decisions are actively reinforcing NVIDIA's private commercial dominance in ways that weren't nearly as prominent during the earlier AI adoption wave. This blending of public research infrastructure with private commercial strategy raises genuinely novel policy questions that didn't arise in quite the same way during NVIDIA's earlier rise. And it's part of why this particular hardware war is attracting attention from policymakers who mostly stayed on the sidelines during the AI chip boom. So what happens next in this hardware war? If quantum computing scales as fast as the most aggressive roadmaps suggest, NVIDIA may end up controlling the connective infrastructure underneath an entirely new era of computing, before most of the public even understands quantum computers exist outside of headlines. The alternative scenario is worth considering too, because it's not guaranteed NVIDIA wins this the same way it won the AI race. Quantum computing involves physics constraints that don't bend to software cleverness the way classical computing problems often do. And if a rival company or a well-funded startup finds a genuinely superior way to integrate classical and quantum systems, NVIDIA's early lead could erode faster than its AI dominance ever did. Quantum error correction remains an unsolved problem at true scale, and whoever cracks the hardest remaining pieces of that puzzle first could reshape who actually controls this integration layer going forward, regardless of how much infrastructure NVIDIA has already built. It's worth examining how rival companies are actually responding to NVIDIA's quantum push, because their reactions reveal a lot about how seriously the industry is taking this threat. Google, with its own deep quantum research history and access to massive internal computing resources through its TPU infrastructure, has continued advancing its Willow chip research independently, seemingly betting that its combined expertise in both quantum hardware and classical AI computing could eventually let it build a competitive integrated stack without needing NVIDIA's infrastructure at all. Microsoft has taken a somewhat similar approach, leaning on its own Azure cloud infrastructure and deep pockets to fund its topological qubit research, while also maintaining a complicated relationship with NVIDIA as both a customer for AI chips and a potential future competitor in quantum integration. IBM, perhaps the most quantum-focused of the major tech giants, given its decades-long specific commitment to the technology, has continued building out its own quantum-centric supercomputing architecture, explicitly positioning itself as an alternative to NVIDIA-dependent infrastructure for research institutions wary of concentrating too much reliance on a single vendor. For now, the clearest takeaway is this. NVIDIA spent nearly 2 decades quietly building the infrastructure that made it indispensable to the AI revolution, and the world largely didn't notice until that revolution had already arrived, and NVIDIA was already sitting at its center. The company appears to be running an accelerated version of that exact same playbook with quantum computing right now, compressing what took almost 20 years the first time into what looks increasingly like a matter of just a few years this time around. Whether that compressed timeline means quantum computing itself is arriving faster than expected, or simply that NVIDIA has gotten dramatically better at executing its own strategic playbook, the practical result looks remarkably similar either way. A technology company positioning itself to control critical infrastructure underneath a computing paradigm shift before most of the world has even started paying attention. The last time this exact pattern played out, the world woke up one day to discover a graphics chip company had quietly become one of the most valuable and consequential companies on the planet. There's a reasonable chance we're watching the earliest chapters of that same story unfold a second time, just under a different name, with a different underlying physics and a much shorter runway before the rest of the world catches up to what's already happening right now, quietly, inside a handful of research labs and data centers most people will never see. If this breakdown helped you understand what's really happening behind these headlines, make sure you like this video and subscribe, because this hardware war is only getting started, and there's a lot more coming worth tracking closely. If you know someone working in tech, finance, or research who should be paying closer attention to this story, send this their way, because the companies and institutions that understand this shift early are going to be in a dramatically stronger position than the ones who wait for it to become impossible to ignore. Thanks for watching, and I'll see you in the next one. None of these responses currently look like a decisive counter to NVIDIA's strategy, largely because none of these companies has NVIDIA's specific combination of manufacturing scale, developer ecosystem reach, and willingness to give away foundational tools for free in order to accelerate adoption across the widest possible range of research institutions and hardware partners simultaneously. But the sheer resources these companies command means the competitive picture could shift meaningfully over the next few years, particularly if any of them achieves a genuine physics breakthrough dramatic, enough to reduce their dependency on ultra-fast classical error correction in the first place, which would directly undercut the core value proposition. NVIDIA's entire quantum strategy company, currently taking a cut of nearly every major AI breakthrough on the planet, also ends up taking a cut of the next major leap forward in computing power. Whether that leap comes from Google, Microsoft, IBM, or a startup nobody has heard of yet. Whether you find that impressive or alarming probably depends on how comfortable you are with one company holding that much leverage over 2 consecutive technological revolutions in a row. For everyday consumers, the more immediate impact will likely show up indirectly, through the products and services built on top of whichever computing infrastructure ends up dominant, faster drug discovery reaching pharmacies sooner, smarter AI systems trained, using hybrid quantum classical techniques or entirely new, categories of software nobody has invented yet, because the underlying computing power to build them simply didn't exist before now. It's worth spending a moment on why drug discovery in particular keeps coming up as one of the flagship applications this entire hardware war is ultimately being fought over. When pharmaceutical researchers try to predict how a new drug molecule will bind to a target protein in the human body, they're essentially trying to simulate quantum mechanical interactions between atoms, electrons, and molecular bonds. Classical computers can approximate these interactions using enormous computational shortcuts, but the approximations get worse as molecules get larger and more complex, which is exactly why so much of drug discovery still relies on expensive, slow laboratory trial and error rather than pure computation. A fault-tolerant quantum computer properly supported by the kind of real-time classical error correction NVIDIA has built its strategy around, could theoretically simulate these interactions with far greater precision because it operates using the same quantum mechanical principles the molecules themselves obey. This is precisely why pharmaceutical companies like Moderna have already begun experimenting with quantum extreme learning machine workflows built on NVIDIA's Q2Q platform, treating this hardware war not as an abstract corporate rivalry, but as a direct pathway toward faster, cheaper drug development. Materials science follows a remarkably similar logic, and it's worth understanding why this particular application has attracted so much serious institutional investment alongside the more headline-grabbing encryption concerns. Everything from more efficient batteries to entirely new categories of superconductors to lighter and stronger materials for aerospace and clean energy depends on understanding how atoms bond and behave at scales classical computers can only approximate. Quantum computers, properly integrated with the kind of ultra-fast classical control systems NVIDIA specializes in, could simulate these interactions using the same quantum mechanical rules that govern the real physical world, rather than relying on the computationally expensive approximations classical supercomputers currently require. Jensen Huang has repeatedly pointed to materials development and drug discovery as the two frontiers he expects quantum computing to transform first, and it's not a coincidence that these are also exactly the applications where NVIDIA's own hybrid quantum classical infrastructure investment pays off most directly and most visibly. For investors and industry watchers, the more immediate impact is a single company potentially compounding its dominance across not one, but two of the most important computing paradigms of this century, back to back, using nearly identical strategic playbooks separated by less than a decade. Then there's the encryption angle, arguably the most consequential and least discussed dimension of this entire hardware war, precisely because it touches every institution on the planet, rather than just the technology sector directly. Most of today's encryption, the systems protecting banking data, medical records, private communications, and classified government information, relies on math problems that are essentially impossible for classical computers to solve within a reasonable time frame. A sufficiently powerful quantum computer, properly supported by real-time classical error correction, could, in theory, tear through that same math dramatically faster. Security researchers refer to this looming moment as Q-Day, and estimates for when it might actually arrive have shifted meaningfully in recent months, with several credible research groups now suggesting the timeline could be measured in years rather than decades. Whoever controls the infrastructure accelerating that timeline, whether through faster hardware, better aero, our correction, or more efficient calibration, effectively holds significant influence over how much warning the rest of the world gets before quantum computers become capable of breaking current encryption standards. That's an enormous responsibility to concentrate inside a single company's infrastructure decisions, and it's part of why this hardware war carries stakes that extend well beyond typical corporate competition. It's worth remembering that NVIDIA isn't operating entirely alone in building this quantum ecosystem, even though its infrastructure sits at the center of the story. Amazon Web Services helped fund the Harvard Quantum Initiative from its earliest days back in 2018, years before NVIDIA's current push began, and has quietly built its own quantum computing division over that same period. This detail matters because it shows the current moment isn't simply the result of one company suddenly discovering quantum computing and rushing in opportunistically. It's the culmination of years of patient, multi-institutional investment, finally reaching a tipping point simultaneously across several fronts at once. Hardware, software, funding, and fundamental physics all converging in the same narrow window of time. When multiple independent lines of progress accelerate together like this, it tends to produce exactly the kind of compressed, competitive landscape the industry is currently experiencing, where several major companies suddenly find themselves racing toward compatible visions of the same future within a remarkably tight time frame. There's a workforce dimension to this story that rarely gets discussed alongside the corporate strategy angle, and it's worth sitting with for a moment because it could end up being one of the biggest practical bottlenecks standing between NVIDIA's current infrastructure build-out and this hardware war actually paying off. Quantum computing requires an unusual and rare combination of skills, deep physics knowledge, specialized computer science expertise, and increasingly, familiarity with NVIDIA's own specific development tools and platforms. Universities have only recently started building dedicated quantum engineering degree programs, and the specialized training required to work meaningfully in this field takes years to develop, even for exceptionally talented students. If NVIDIA's strategy of embedding its tools into academic curricula and research pipelines succeeds, it effectively means the next generation of quantum engineers graduating from these programs will already be fluent in NVIDIA's ecosystem by the time they enter the workforce, extending the same kind of talent pipeline advantage that helped cement CUDA's dominance during the AI boom. where an entire generation of computer science graduates learned to code specifically within NVIDIA's software framework before ever seriously considering alternatives, largely because their professors, textbooks, and university lab infrastructure had already made that choice for them years before graduation. Some universities and companies have already started responding to this looming talent shortage, launching new fellowship programs, specialized coursework, and industry partnerships aimed at fast-tracking the next generation of quantum engineers, but building that pipeline at the scale this moment demands will likely take years longer than building the underlying hardware itself. This talent pipeline dynamic deserves particular attention because it's one of the least visible but most durable competitive advantages a company can build. Hardware specifications can be matched or exceeded by rivals within a product cycle or two. Software ecosystems can theoretically be replicated given enough time and investment. But an entire generation of engineers trained to think in a specific company's frameworks, fluent in its tools by muscle memory rather than conscious choice, represents a competitive moat that takes an entire career cycle, often a decade or more, for a rival to meaningfully erode. This is precisely the dynamic that made switching away from CUDA so difficult for AI researchers, even when technically comparable alternatives existed. And it's exactly the dynamic NVIDIA appears to be deliberately engineering again inside quantum computing, this time starting even earlier in the technology's development curve than it did with AI. It's also worth stepping back and considering the historical pattern this entire situation fits into, because NVIDIA's approach here isn't actually unprecedented, even if the scale and speed of execution feels remarkable. Throughout the history of computing, the companies that ultimately captured the most value from a new technological wave weren't always the ones who invented the core breakthrough. IBM didn't invent the personal computer, but it dominated early enterprise computing by controlling the standards and infrastructure businesses depended on. Microsoft didn't invent the graphical user interface, but it captured enormous value by becoming the default operating system layer that software developers built around. NVIDIA itself didn't invent deep learning, but it captured the lion's share of value from the AI boom by becoming the indispensable hardware and software layer underneath virtually every major breakthrough. This pattern, where infrastructure control matters more than raw invention, appears to be repeating itself once again with quantum computing. And NVIDIA clearly understands this historical lesson better than almost any other company currently operating in the technology sector. The next 12 months will likely tell us far more than the last 12 did, as national laboratories, quantum startups, and rival tech giants either fall further into NVIDIA's ecosystem or find genuine ways to route around it entirely. Either outcome will reshape how the next generation of computing power actually gets built, and who ends up controlling access to it, which is exactly why this quiet hardware war deserves far more attention than the modest headlines it has generated so far. Let's talk about what specific milestones are worth watching over the coming months, because they'll tell us far more about how this hardware war is actually unfolding than any single press release could. Watch whether IBM successfully demonstrates genuine quantum advantage on its promised 2026 timeline, because a clear, independently verified result there would be the single biggest validation the industry has seen yet, and it would immediately raise the question of whether IBM's own integration infrastructure could compete directly with NVIDIA's. Watch whether any of the major photonic quantum companies successfully complete their large-scale system integration efforts, because a working large-scale photonic system would represent a meaningfully different competitive path than the superconducting and neutral atom approaches currently receiving the most attention. Watch whether Microsoft's topological qubit research produces another genuine breakthrough beyond its initial major-on-a-chip announcement, because sustained progress there could eventually reduce the entire industry's dependency on the kind of intensive classical error correction NVIDIA has built its strategy around. And watch whether any serious rival to Q2Q emerges from an unexpected source, because history suggests that genuine disruptions to entrenched infrastructure dominance often come from directions nobody was watching closely enough. Sometimes a small startup nobody had heard of a year earlier, sometimes an open source community effort, and occasionally a fundamental shift in the underlying physics that makes an entire existing integration model obsolete, essentially overnight. There's also a broader question worth sitting with as this story continues to develop, one that goes beyond which specific company ends up capturing the most commercial value from quantum computing. As increasingly powerful hybrid quantum classical systems come online over the next several years, they'll be applied to genuinely consequential problems: drug discovery, material science, financial modeling, and eventually encryption-breaking capabilities that could reshape global cybersecurity. The company, or underneath these systems, will have an outsized influence on how quickly these applications develop, which research priority, get funded and accelerated, and ultimately, who benefits most from the transformative potential this technology promises. That's a responsibility that extends well beyond quarterly earnings reports and competitive positioning. And it's part of why so many people outside the immediate tech industry, from policymakers to ordinary consumers, should be paying closer attention to a story that currently reads, on the surface, like just another corporate hardware announcement buried among dozens of similar headlines. It's worth acknowledging the genuine skepticism that exists within parts of the physics community about how quickly any of this will translate into real-world commercial impact, because a balanced view of this hardware war requires taking that skepticism seriously rather than dismissing it. Some researchers point out that quantum computing has already lived through at least one painful hype cycle, back when early demonstrations in the late 2010s and early 2020s generated breathless headlines about quantum supremacy, only for the practical follow-through to arrive far slower than the initial excitement suggested. Showing a quantum computer can outperform a classical machine on a narrow, artificially constructed benchmark problem is a very different achievement from showing it can outperform classical machines on problems that actually matter to businesses, governments, or scientists. And that gap has tripped up plenty of promising technologies before. NVIDIA itself has an obvious financial incentive to hype a technology. It has now invested billions of dollars into supporting, and university press releases about breakthrough results don't always survive the slower, more rigorous process of independent replication that true scientific consensus requires. None of this necessarily means the current wave of momentum is overstated, but it is a reason to watch the next 12 to 24 months carefully, rather than assuming the most optimistic timeline currently being discussed is automatically the correct one.